This class I will try to convey some of the topics that we are interested in the area of hydroclimatology and water resource. So let me share my screen first. So can someone confirm that my screen is visible?
Yes, it is visible.
Yeah, and sometimes it creates a problem also while going from one slide to another one. Can someone confirm that it is second slide?
Yes, it is.
Okay. Okay, fine. So once again, welcome. So in this talk, what I'll try to convey you some of the applications of AI and ML in hydroclimatology, and also to some of the water resources issues as and where it found to be suitable to apply. So as I can understand, the class is from a diversified background of their own domain. So this hydroclimatology may be a new word for them, but you know it is one of the important area in the bigger domain of earth science. It is an interdisciplinary area where we try to find out the link between the hydrological variables and climate science. Now, why it has become important recently is that if there is some change in the climate and if we can identify their association with the hydrologic variables, then the impact of on the hydrologic variables that we can identify. And since one step ahead would be that how our water resources can have been affected to that in that one, that also can be understood. So in this particular talk, I will try to group the different areas where I will just show you that how the application could have been made, and it is basically the acknowledgement goes to my research group, my research students who have done the work under my supervision. So three broad areas that we are going to discuss today is the first one is the rainfall and stream flow prediction. This rainfall stream flow are the what called the primary hydrological variables. So where and how their variability can be assessed, that we will see. Secondly, we will see the hydroclimatic analysis where some sort of global climate variables we generally try to extract their pattern, try to extract their information, try to use that information in this in the hydroclimatic analysis as well as their prediction. That we will see. And also I'll try to cover up some part of this soil mass retrieval using remote sensing data. It is again a different domain with the remote sensing applications, but as you know that through the satellite we can collect the data set, the huge data set we can collect, but many times our target variable to extract the information for our target variable, there is a lots of noise and other things are there. So how this AI/ML can be utilized in that kind of problems also. So when I talk about this AI/ML, some of the tools that you might have already heard by this time in this course itself, that there is genetic algorithm, genetic programming, support vector machines, support vector regressions, random forest, ANN, then also the graphical modeling approach, deep learning approach, and there, of course, there will be some more things that comes. I just try to cover some of them, and then you will get some idea about that how the things can be taken forward. So as I told, that first thing that we are going to discuss about some of the rainfall and stream flow related issues. So here one of the very early application that in our group it is made in case of the stream flow prediction. So stream flow prediction here, in this case we have taken the study areas in the Mahanadi River Basin, and in that Mahanadi River Basin up to this area that you can see here is the Hirakud reservoir. So there are some inflow that happens. So few kilometers upstream here. So maybe approximately 50 to 100 kilometers upstream, there is an area called Basanpur. So there is a stream gauging station here in the Basantpur. The records are available there. So we tried to model that stream flow that at a monthly scale and try to find out that how the variability of the stream flow can vary between different months. So we have taken different months means here mostly we have taken that June, July, August and September, and also we have included October also, which is a post monsoon month, but still the stream flow variation is high for this particular months also. But here the target is taking the large scale indices. So large scale indices, though this is a very brief slide that I mentioned, but I think some of the thing we can discuss also as I am going through. The thing is that we can just take up that El Nino and Southern Oscillation that is now has come in our news and media also. Most of the time during the summer months we heard that the El Nino status is this. So what the India can expect in this coming monsoon. That kind of news has started already coming in. But way back, say before 1 or 2 decades, it was not the situation like that. When we tried to find out the relationship with respect to these hydrologic variables such as stream flow. It is not only that so there are other large scale indices are also available, which are from the tropical Indian Ocean. It is called Indian Ocean dipole. And as you might be knowing, this kind of large scale indices are the coupled indices. This coupled means there are two phenomena happen. One is called oceanic phenomena, other one is called atmospheric phenomena. So the oceanic phenomena generally reflected through the sea surface temperature variation, and the atmospheric phenomena generally by wind field or pressure field like that. So ENSO, that is El Nino Southern Oscillation, is also a coupled one, which is the El Nino is the oceanic component and Southern Oscillation is the atmospheric component, which is coming from the pressure field. Similarly, in case of Indian Ocean dipole also, there are two such things. One is called DMI, Dipole Mode Index, which is the oceanic component, and equatorial Indian Ocean Oscillation, which is coming from the atmospheric component, and it is from the wind field. So wind field in the equatorial Indian Ocean region, and its negative anomaly is basically known as the equi-wind. So we call it at equino index. So you see in this particular slide there are some such EN or EQ are written. So these two are basically those large scale indices. But the first challenge that comes then from which inputs that we can consider, and it can happen in many similar type of applications. So what input should be good and what should be the best network architecture that we should take. This network architecture means the network for this artificial neural network that I mean to. And there are, to decide the best network, there it is called that genetic algorithm has been utilized, and it is trained in numbers of such networks are trained, and we found out that which one is basically turn out of the good thing. So this is also known as the ANNGA approach. So where the architecture is optimized through genetic algorithm, and ANN is then utilized to extract the information from the input variables and put it in the target. So here you can see that so far as the different months are concerned, over different years, there is significant variation in the month of June, July, all these months. So, and what we have seen that for the different months, when the base network architecture is different, inputs are also different. So there are some sort of promise from this approach that we can see at least that how much in the stream flow that can happen in these different months. Like June, July, August, September is the monsoon months that you know, but still October is also showing some significant stream flow in the month of October as well. This application is taken forward for this monthly stream flow as well, where we call it as a support vector regression. And as you know that the support vector regression is basically one of the approach where the input variables it is transformed to some hyperspace, and we try to regress it in that hyperspace, and then we take it back to the actual time series scale. So one of such example is shown here in this right hand corner. There you can see that there are two inputs are there, and we can so only for two inputs we can just show such this kind of thing as a pictorial demonstration. And if there are more, so concept can be of course extended, but pictorial representation not be possible. So here you can see that how this Hubble space there are some it varies over, and these black stars that you see, those are basically the data points how these inputs, the pair of inputs and the output how it varies. So it is there are different other approaches are also there. You may be knowing that this box Jenkins approach, which is known as there is some background noise coming from somewhere. Okay. So that is called the ARIMA, so auto-regressive integrated moving average model. So there are different such models are tested, and the base model is identified, and then we have seen that whether how good this support vector regression, that is one of the machine learning approaches compared with that purely statistical model of this ARIMA. So this the benefit of this machine learning approach as compared to those linear model is that sometimes if the relationship is purely linear at the different scales, then it is okay. But sometimes it is not due to the several factors. So when the stream flow is the low stream flow regime, that medium stream flow regime and high stream flow regime, basically the influence varies depending on the watershed condition and all. So there, more it varies the benefit of support vector regression or this kind of model. It is realized in a much better way. Now I'll give you some sort of idea about these extremes and how to extract it from these global climatic fields that we'll show. And some of the things that I was discussing before, here also there are two things I've considered. One is El Nino Southern Oscillation, and other one is Indian Ocean Dipole mode. But the idea is that these are established with some sort of evidence that there are some influence, but the overall thing that we have done is that is it the only these are the two things that can influence the hydrological extremes in some location across the world. So we have taken the India as our target thing, and so there below and above normal events if we just pick out, and so should we see that only these are the two things that can influence, or the influence can come from some other domains also? For those who are not aware of these things, it is not only these are the two indices, there are other indices are also there, like North Atlantic indices, then there is Pacific Decadal Oscillation. There are many such large scale indices are there. But thing is that if I just pick out some of the basic climatic variables, including sea surface temperature, then are these the only domain where I can see some association, or there could be some other regions also may pop up to be important? And then we can see that how the information can be extracted from that. So this is the overall idea behind the what is written here as GCP, the global climate pattern for the hydrological extremes are basically tried to extract it. So what we have done, we have picked out not only the sea surface temperature, there are total 6 different variables are considered, out of which some are global and some are local depending on the nature of this variable. For example, the sea surface temperature, it is global, and then surface pressure also taken as global. This air temperature, wind speed, total precipitated water and relative humidity, these are taken as the local variables. So local means, I mean, in a continental scale. So, and this global means the entire globe has been considered. So these are some of the variables when we consider, and then we have taken the rainfall data from India Meteorological Department, and then we just consider that if there is some above normal event and the below normal event, how they are in those particular years, if we just speak and want to see something, some information, if we check, if we want to extract from the global field and the local field, then how they compare to each other. Before that, one more thing is that how to define that extremes. So this is one of the thing for this Indian hydroclimatology that we have put. It is called the SPAI. The full form is Standardized Precipitation Anomaly Index. So the Standardized Precipitation Anomaly Index is one such index from which we can identify that how much it is deviating from the normal situation, and its counterpart is called SPI, the Standardized Precipitation Index. Now, depending on the how much is the seasonality is there in the time series, the benefit of SPAI can be realized more. What I mean, it has again altogether a different presentation could have been given, but in very brief, I just want to mention that is SPI, the Standardized Precipitation Index, is basically good to identify the deviations from the normality or from the normal value if the seasonality is not there. Whereas the SPAI can consider the local climatology, and it gives better picture or more clear picture how much the extreme is. If I just give you one example, you know that Indian precipitations are more during the June, July, August, and September in these 4 months. Whereas, say, for example, if I take some months like December or January, living one or two places in southern tip, most of our locations in our country, they don't have much rainfall in these months. Now, suppose that one of the January is having some rainfall and some other, even if the rainfall in the month of January is zero, then SPI will give you a very, very low value where it sounds like it is a highly drought month. But actually, in the real scenario, since our climatology is like that, we don't expect much rainfall in the month of January. So it is basically not a drought, and our government and our community, our society is not worried about it whether we receive any rainfall in the month of January or not. But this thing is not distinguishable in case of SPI, which is a Standardized Precipitation Index, but it is distinguishable in case of SPAI, that is Standardized Precipitation Anomaly Index. So simply because we have considered, we are not using this raw rainfall series, we are using its anomaly. The anomaly itself is the deviation from the mean, so that gives that benefit. But there are some more deviations from the SPI and SPAI. The thing is that if you take the raw rainfall series, you know that series will be always positive, non-negative numbers. So there, the distribution can be something like a gamma distribution also. And in fact, for SPI, we use the gamma distribution only. But when we take the anomaly, so these anomalies can go either positive or negative direction also, and we have shown that this T location scale probability distribution can be fitted well to this kind of anomaly series, and from there we convert it to the cumulative distribution function of this inverse standard normal distribution to find out the final index. And now finally, once we get this SPAI, if it is less than 0.8, or then we call it as a dry, and if it is greater than 0.8, then we call it as wet. So with this classification between these two, now we want to identify and characterize the global climate pattern for different extremes. So that here the different extreme means we have taken the two things first, and one is called the dry, another one is the wet, and of course the rest of the things are normal. So what we do for each of the dry or wet event, that at the temporal scale of 3 months, the 3 months standardized and anomalies of this climate variables are obtained at 3 months lag in the all grids across the globe. Across the globe means when we talk that whenever we are considering the global variables, but if it is local, of course, in the continental scale. The mean climate anomaly for all the dry events are determined event-wise and averaging this concerned climate anomaly over each grid, and then the same thing for the wet months as in sorry. Yeah, and then for all the wet months also, we separate out all these climate fields which are basically for the wet events, that is when the SPI is more than 0.8. So in this way, when we just differentiate between these two, and we see the maps showing the global fields of this anomaly of the difference between the dry and wet. So we take the difference, that how the average map looks like during the dry years and the average map looks like during the wet years, and we take this difference between these two. And that anomaly is very clearly visible, that when the difference is more, of course, those areas are more significantly important to extract these signals. One such typical example is shown here, so far as the sea surface temperature zones are concerned. So if we see that there is a very clear picture of this, the western or eastern tropical Pacific Ocean is warmer than normal, whereas the western part is colder than normal. Similarly, other parts in the northern part we can see, so there are some things. So few things are already known. For example, as I was mentioning that ENSO, the ENSO is basically an event where you can see where I show my mouse here. So it is the equatorial Pacific Ocean toward the eastern side. So there, when it is anomalously warming up, that is called the El Nino years. So in this process also, we could have identified successfully that the ENSO is having some influence on the dry or wet events in India. Now the next question is that this not only the ENSO part, there are other areas are also this showing some sort of importance where those information can also be considered. So those things are shown by different rectangular zones in different parts of this world. And this is for sea surface temperature. Now, if I take that surface pressure, then also you see there are some areas in this tropical Indian Ocean becomes important. Of course, some parts of this Pacific Oceans are also important. So in this way, we have picked out wherever the difference is very high, we picked out those regions for that particular variables from the global, as well as for the others we have picked out for those information which are basically the local also. For example, here it is air temperature in the first panel, and the wind speed in the second panel, and the total precipitable water in the third panel. So interestingly, you will see in the middle panel when I come, it is basically this is the one where it is the equatorial Indian Ocean oscillation is reflected through the wind field in this, approximately in this domain itself. And whereas the total precipitable water, when it is more in this region, it indicates that the southwest monsoon will carry more moisture towards this Indian part, and it will create more rainfall. So something which is already we know, for example, this ENSO and Equino, as I was mentioning that. Apart from that, there are other regions are also there which becomes important. So in this way, what we have done, in total, there are total 15 such different variables are there, which we can pick out from different domains of this globe, and that basically forms this global climate pattern for the target variable here is that Indian summer monsoon rainfall. Now the thing is that in this way, if we just identify the different variables, so can we just extract the information from these and find out a concise information and put into the one. So what we have done first is the dimensionality reduction has been done through this principal component analysis that you might be knowing, and then those inputs are given in some modeling approach. Here I'll show that one of the application is that SVM that I'm coming a bit later. So now thing is that if you start with just 15 different variables and proceed to this principal component analysis, you will also end up with the 15 different principal components. But you know that the first few principal components will carry most of the variability in it. So that we can test that how many such principal components is sufficient for you. And in this one, I can show you that there are 6 such principal components that we can take, and this will be considered as this one. So now the question is that we already know some of these teleconnections, some of these hydroclimatic indicators like that ENSO and Equino. We can call it as a known hydroclimatic indicators compared to the GCP, that is global climate pattern, where it is even more than that. So how much benefit I do get? So if I consider all these things, so that comparison can also be made. So this is the overall thing, and as I was showing you that this principal component analysis, how many such components can we consider to get this maximum performance, and this performance is there is a called the contingency coefficients through which we can calculate. And we have seen that if we take approximately 6 components, if we take, then it is sufficient to consider the full thing. Now comes that the domain that where the actual we have applied the sum of the machine learning tool to understand for these different categories. Now we have 3 categories as I mentioned. One is the dry, other one is wet, and the third one is that normal one. And so far as the support vector machine is concerned, it is basically good for the dichotomous categorization classification. So there are 2 such SVMs are trained in this way. One is called SVM1 and other one is SVM2. The SVM1, what does it do? It classifies between the dry and not dry, and whereas SVM2 is classifying between wet and not wet. Now both the models are run. Suppose that if the first model says that it is dry and second model tells it is not wet, then the final conclusion is easy. That means second one says not wet, first one says dry, so that I can directly conclude it is a dry thing. Similarly, all these combinations can lead to, there are 4 such combinations are possible from this 2 model output, and we can, apart from one, we can conclude it very easily that if the SVM 1 says that not dry and 2 says that not wet, then we can conclude that it's to be a normal. But suppose that it is a numerical thing, so anything can happen. So this SVM1 says dry and SVM2 said wet, then we call it as it is the cannot be determined case. It is an indeterminate case in that one. But though it is possible, logically it is possible, but we have seen in our application, so no such events is coming where it is coming to that this kind of classification. No, it is one, it is dry, and other one it is saying it is wet. So with this combination of this support vector machine, and there are some evaluation parameters are also there. I am not going into that. So there are some problems we have seen that this dry and the wet events can be identified, particularly if it is really dry or really wet. But what we have also seen that is a drawback of this kind of thing, that model is generally not classifying many things towards the normal part. So that normal prediction is not there. So what it raises that it is called the false alarm ratio in the statistical domain. So the false alarm is also increasing. But so far as the actual dry or actual wet events are concerned, their prediction performance is good. Okay, so with that one, but also there is another comparison that whether we can take this entire climate field or we take only the known things. We have seen that there are some more improvement when we take this global climate field. Well, so let me proceed to the third one that I was telling the different application of different techniques. So this is one of the techniques that we have recently applied to this long lead prediction of ENSO itself. It is called the ENSO Modoki index. So sometimes what happens, though the researchers tries to predict those indicators itself. So for example, that ENSO is utilized as an input to predict that variables in some other field. But in some cases, we want to predict that ENSO in itself for another 6 months or another 1 year, or even sometime even more, that how it is going to vary. So if I can tell that one, then that information can be utilized in different fields. So one such attempt that was made from our group is called the long lead prediction of ENSO Modoki. Now, what is the difference between ENSO and ENSO Modoki that we can see first? It is basically, as I was showing you earlier, that this part, the C domain approximately, is basically where we look at that ENSO events in the different domains. And so far as El Nino Modoki, which is abbreviated as EMI, it is basically the sea surface temperature anomaly at the location A, which is the tropical specific ocean, we call it as. This one minus the half of the SSTA in the domain B minus half of the SST domain in this domain C. So this is an already established equation from which we calculate the El Nino Modoki. Now this El Nino Modoki, what people generally see is that it is, this is basically from the Japanese scientists. They have recently observed that this, if we instead of using this El Nino, if we just use this El Nino Modoki, maybe some of the linkage with the different hydrological phenomenon is much more. we are not going into that debate, but what we are trying to do in this particular domain is that what kind of persistence that this kind of climate indices may have, and that persistence, can it be captured by some machine learning approach or not. So that is the overall objective of this one. So we have utilized some of this algorithm which is effective. We already know that for the multivariate linear or nonlinear system it is effective. So some of the models that we have tried, and we just see that whether how good this performance could be. Before that, what is existing picture? Existing picture means before we apply this machine learning thing, what people are doing now. So, for example, this Bureau of Meteorology Predictive Ocean Atmospheric Model for Australia, WAMA it's called as, they generally give the prediction up to 6 months in the lead with a correlation coefficient of approximately 0.6. Whereas the Effect Climate Center, APCC, multimodal ensemble prediction they do, they give a prediction in advance of this 4 months with a prediction of 0.8, and there are other organizations, they give the different prediction lead time with the different performance. One thing is obvious that if the prediction lead time increases, the performance will decrease. But at the same time, we have to go for a trade-off between these two. So this is the existing thing. Now we tried our this machine learning application to this problem, and then we just see that what could be what improvement, if there is anything that we can show or not. So this kind of the global system, when it is changing, these are all basically coupled. So what we have done, the monthly input data from the sea surface temperature anomaly, sea surface height anomaly, and soil moisture content all over the globe that has been considered. Now this variables globally when we consider, and then we take the significant correlation zones for each variable through this Kendall's tau. This Kendall's tau again is different from this the Pearson correlation coefficient, as if that it is not only the linear association, it shows some sort of, if there is any nonlinear association also that can be reflected through this, which is not possible in Pearson correlation coefficient. Then we go for this the dimensionality reduction. Again, instead of using this principal component analysis, we use that supervised principal component analysis. Now, what does the supervised principal component analysis do? It is called an SPCA. Is that we identify the target. Now, rotate the access system of the input variable in such a way that the first component gives the maximum information for the target variable in hand. Okay, so if the target variable changes, the same set of input will give you some other combination. So to make it the maximum association with respect to the target variable, that is how it is supervised. So supervised with respect to the target in the case. So here our EMI series that is there, that is the target. So we want to take these variables from all over the world again, and we want to find out, we want to do some dimensionality reduction via this SPCA, and then we apply this machine learning algorithm. And here we have applied the support vector machine and random forest at a lag of 6 months, 12 months, 18 months, and 24 months. That is from 6 months to 2 years lag of the input. So lag of the input automatically indicates that lead of the prediction. So 6 month lag information, if I apply and check, that means I am getting a 6 month lead performance. And of course, there are some k-fold cross validation technique is used to identify how the model performance is for different time period. So again, this is how the different zones and domains are popped up depending on the significant Kendall's tau. So far as sea surface temperature is concerned, soil moisture content. Soil moisture content is less informative, as we can see, as compared to the sea surface height and sea surface temperature. But still, there are some regions are there which are important. And then, of course, the maximum input it comes as a SPCA coefficient. This SPCA coefficient means how these things, if your target is EMI, what are the different coefficients that it comes, so that it is basically giving the weightage to the final input variable to the things. So here you can see that, of course, the major signal coming from the sea surface temperatures only, and of course some signal from sea surface height and soil moisture content. Similarly, for the 6-month lag, 12 months lag, and I'm not showing, but there are some 18 months and 24 months lags as well. So now the thing is that if we just take each and every month as for the target variable, the fluctuations will be very high. There is some local fluctuations will be there. So what generally is done is that we take some running or the smoothing effect through that moving average, and then the local fluctuations is go up, and we are generally able to see that what is overall change of the index in time. So here you can see as an example, there are 5 months moving average, how it looks like for this different the blue series that you see. This is basically how it is varying once it is going below 0 and above 0. So these positive and negative anomalies are there. That index value is there here. Now, if we just compare for these different folds, here you can see that 4-fold cross validation is done. That means we use this one as a development period and this one as a testing. Similarly, the testing periods are taken from different domains to check that how the performance varies from this development and testing period. So for different folds, the results are shown here in terms of the different performance metrics, this RMSE, the degree of agreement and correlation coefficient. There are different indices are utilized for the lag 6 months and for the lag 12 months. So what happens for this 18 and 24, though we have carried out and it is not shown here. So from 18 months is still okay, but 24 months is not that meaningful or useful. But up to 12 months lag, if we use the information, so there are few things which are being captured through this support vector regression model, and which is good. And particularly when you go for a smoothing of the series through this moving average, the performance is marginally better again as compared to the totally without moving average. Now the thing is that the case by case it was checked that how this phase and the magnitude. Phase means whether it is positive or negative, and magnitude means that what is the value of that index for different phases of this positive and negative EMI that has been checked from this from the April 1983 to recently that April 2017, and these are all from the testing period, not the training only. So whenever it falls in the training period, then with 6-month lead and the 12-month lead, how good these prediction performance are. So there are these different ticks are having different meaning. So if there are 3 ticks, that means it is able to capture both the phase as well as the magnitude. If there are 2 ticks, it is able to correctly catch the phase but not the magnitude in that accuracy. And single tick means it can catch only the phase, not the magnitude, and cross means it cannot. So in most of the cases what we have seen, it is either capturing both the phase as well as magnitude, or at least it can able to catch the phase very rightly. So even at the 12 months lead time effect, and then it is giving some information. So this is very useful to see something what is going to happen at least the 12 months before. Given the lead time, it has become very, very useful to the community. So I discussed most of these findings, how is it varying from 6 months to 12 months, and of course it is not as good as to carry out this or make this prediction useful at the 18 months and 2 years in advance. But up to 12 months, which is still not available, this kind of models can be utilized properly. Next, let me show you some application in case of remote sensing. Here we are trying to retrieve the soil moisture using the quad polarized synthetic aperture radar, which stands for this SAR, the synthetic aperture radar data from the radar imaging satellite RISAT-1. So this RISAT-1 is basically our indigenous satellite by ISRO, and it was there are 2, RISAT-1 and RISAT-2. RISAT-2 is for some other purpose, and RISAT-1 is for this kind of natural hazards and all. So there are different modes this satellite can be operated, and some of the things that can give you a very fine resolution information can come. But before I discuss about this satellite details, the soil masters, those who are already aware of, they know that how important is this variable, so that it is called one of the essential climatological variable, abbreviated ECV, due to its critical role in the land atmosphere feedback. For example, that it influences the variability of the evapotranspiration and runoff, then floods and droughts, forecasting the water supply in the groundwater system, temperature variability and occurrence, persistence of the heat waves, and for generation and the location of the precipitation and all. So this is, so for any climate model particularly, this a better estimate or the good estimate of the soil moisture is a very valuable input to that. And the final resolution is, of course, is one of the big challenge, because soil moisture is one of the thing that can vary even over few meters. So if you just see that what is the soil moisture at a particular location, if you just go few meters, it may change. So the spatial variability is very high. Means even it is higher than many other variables that we know, even from the precipitation, air temperature. Those things also vary, but soil moisture varies in a even much in a higher spatial resolution. So what we do generally, we can go for some in situ measurement, but the in situ measurements have lots of problems that you can understand. One first thing is its spatial variability. So we need kind of to characterize even a small field. We need to characterize its spatial variation. We want to feel sometimes it is next to impossible. We always need to go for some assessment. For the large scale assessment, we need to do, but still for that one, the large number of samples has to be collected and then tested in the laboratory and to understand this thing. That's why it is very much time, labor, and cost intensive. And it also depends on the type of soil, it is functional characteristics, atmospheric condition, there are high maintenance of these equipments and all. If we want to go for some sensor-based measurement, those things are there. So, but when you go for the satellite-based estimate, some of these problems are solved, of course, because we can see the larger area, and depending on the resolution, it can go that much fine-tuning thing. But one of the major drawback again from that one is that we get lots of information, no doubt, but linking it with the ground truth and converting that satellite data to a real soil moisture field, it becomes a challenge. So both sides there is a pros and cons. So what we can do is that if there are some satellite that is available which gives you a very good resolution, and if we can establish some relationship, identify some relationship with that data and this ground soil moisture content, then it will be really meaningful and very much useful. So towards that, one such attempt is to use this machine learning approach, whether this data can be analyzed through that one. So some of the details about the research one that I started is that it was launched in 26th April 2012. But research 2, even which was supposed to be launched after this, it was launched before this one. Rather, this schedule was even before 2012. It was supposed to be in 2010. But anyway, for somehow it was delayed. But when the data started coming in, there is a huge data we came, and there is one mode is called the FRS mode. That is important, the fine resolution strip map mode, and it gives a really very high resolution. For example, it ranges from 3 to 10 meter resolution it can provide, which is very useful so far as this kind of studies are concerned. Again, one drawback is that it has a temporal resolution of 25 days. So this 25 days means revisit time. So once we get one image, then it will again may come after 25 days or so. But sometimes it depends on that incident angle. There is also another term. So from the incident angle, some of the areas we can just see. So those are some of the technical details from this data thing. Okay, one more thing that I will do for a proceed further. It's called the quad polarized data. This quad polarized data means it is basically having two. It is an electromagnetic wave. It is generally emits in two directions. One is called the horizontal, other one is called vertical. And it is an active one. So it receives, and this when it is releasing in the horizontal direction and receiving in the same horizontal direction. It is called the HH. And similarly, four such combinations are possible if there are two such directions, one is horizontal, one is vertical. So what we do get from here is that this HH and VV, and these are called the polarized one, and then HV and VH, these are called the cross polarized information. Earlier what happens, there is only single polarization was there, that is called HH, and this HH is one of the most informative variable so far as the soil moisture is concerned. Now over the time, since the quad polarized information has come, that is other three polarizations has also come. Now the idea is that whether we are getting some extra information from these other three polarizations or not. And of course the main question remains, that is how to extract again this information from this one. So from the satellite we have four such inputs, and also we have considered some of the ground information like the soil texture and its sand, silt and clay content also that we have considered. So idea was like this, that the satellite process, we book the satellite. Book the satellite means it doesn't operate by default in the FRS mode, because it is a huge data intensive thing, as you can understand from the spatial resolution. So once we book this one, they run on that day that satellite in that mode, so that later on we can collect that satellite images. And we then went to these nearby areas of this Kharagpur and we collected this information from approximately 375 locations, and that satellite passing time is 5 p.m. And then approximately 1 hour before and 1 hour after, we collected all this information from different groups. And you can see that some red circles are there. From there we collected the soil sample to find out how much is the moisture content in that at the time, particular time instances. And there are some stars also you can see where we have collected that soil samples to calculate its sand, silt and clay content to know the soil properties. And then all these things we have just given as an input, and to find out that how there are things are there. Again, there are some more technical details are there. For example, the permanent wilting point, it is some threshold value of this soil moisture content. If it falls below this one, then vegetation cannot accept any more water and it will eventually die. And any soil moisture that is available above this permanent wilting point, it is called the available soil moisture. So again, these are the terms, the absolute soil moisture content or the available soil moisture. So these are the different terms from where we can just see that which one is more kind of estimation can be done for that one that we have checked. This is one of the pre-processing from the DN value. That is, DN value means the digital numbers for each pixel. And this is basically done by ISRO itself, and they supplied the data for this sigma 0, and this sigma 0 is called the radar backscatter coefficient. So this is the value from where we can just when it came to us, this preparation was done at that ISRO itself. So as I was telling, if I just take two data, so that initially the 25th October and 27th October was there. Their incident angles are like this. So again, there is one methodology that is called the incident angle normalization. So that there are some, though I'm not going in that detail, there is a Jirvi et al. They gave some theory from where we can just take this the backscatter value to a common incident angle. So that has been done. And then we just put it in the suborbital meshing domain. There are some theoretical part here you might have already covered in this course itself. So from there, different methodologies has been utilized: suborbital meshing, genetic programming, random forests, etc. And then there are different cases are considered. Here you see there are total 13 cases are considered, and with different input combinations. The first case, all four quad polarized satellite information and also the soil properties as the sand, silt, clay. And in this way, we generally take out one, put one more extra, just to find out that what is the importance of that particular input. As I was telling, one of the things is that HH earlier, so far before this one, we used only that HH information for this kind of thing. And one more new thing is called the RVI, which stands for the Radar Vegetation Index. And it is also again calculated from this cross-polarized this information and this thing. Instead of considering all four, can we just utilize only RVI and just check how the information is coming up? So all these different cases of this different combination of this input has been considered. and they are different in the validation period, how their performance is, that has been tested. And I can take you to this final thing. This is one of the satellite imagery plate that you can see, and where the final thing, when the model is already trained and developed with those ground truth locations, and then we apply this model throughout this panel, and we can see that how this soil moisture variation looks like, and it is of that resolution of approximately 5-meter resolution. And you can easily see that near the river valley kind of thing, which is soil moisture content is more and it is dry in some other part. And there are some white patches also you can see, and approximately this is the IIT Kharagpur locations. These white patches means the ground is not visible. Either it is covered by a very big canopy, or it is covered by some not a bare soil. Okay, and it can penetrate up to 30 centimeter of the vegetation cover because of this property of this area, but it cannot penetrate more than that. And this area is mostly, that is cultivated zone. So you can see that there are some lines also. I don't know how good it is visible to you at your end. So these are the highways there, and it is also covered like this. But the color tone that you see, apart from the white patches, the blue to yellow, so I should say that yellow to blue. So yellow is a very less soil moisture content, and blue is a high soil moisture content. So so far as the spatial resolution is concerned, it is really amazing. So far as earlier, we generally, now the era 5 has come, which is resolution is slightly better than this. Earlier, when the era interim data was there, say for example 0.25 by 0.25 is the resolution by lat long. Now 0.1 by 0.1 has come, but still this resolution is much more appealing and much more finer for this kind of estimate. And this is for earlier is from 25th of October, this is 27th of October. Okay, coming to the next one is the deep learning approach, and here in this application we have showed that 1 day to 5 day ahead rainfall prediction using multiple hydroclimatic inputs. So we just see that one from this previous some information, we just take this as an input, and can we say something for what is going to happen in the tomorrow to up to 5 days. Nowadays in the smartphone we have already some information we do create that is called the weather outlook that we have seen in the coming 3 days that we have seen. So here with the availability of this deep learning and this input variables, can this relationship can be identified or not, and that is the target here. So here the thing is that there are few basic things comes, and maybe you have already seen some of this topic in this course itself. So our primary objective for this particular task is that we already know that there are different primary meteorological variables that is available to us. Can some information be extracted from there to say something about the more complex variables? Rainfall is one of the example for the coming days. That is the overall thing, and it has some applied in some other studies also. Some of the studies are shown here as an application of this kind of analysis. We have taken different city-based measurement, and in this specific study, the 12 different cities in Maharashtra has been considered, and there we are just using an hybrid approach of this Convo 1D and MLP algorithm, and from there are 9 causal variables are considered. These causal variables are maximum air temperature, maximum relative humidity, minimum relative humidity, geopotential height, long wave radiation, sea level pressure, zonal wind, meridional wind, and the previous day's rainfall. So these things has been considered, and there that these things are available at some different lat long resolution, either from the climate model simulations or from this IMD data. The idea here is that whenever the GCM or any climate model, they try to simulate some of these meteorological variables, their skill is generally good so far as the primary meteorological variables are concerned. This primary meteorological variables means, for example, the air temperature, relative humidity, pressure, wind field, this kind of things. When it comes, it is little bit more skillful So as compared to those variables like precipitation, soil moisture, that kind of thing, it is not so good. So idea is that can I utilize the potential of GCM where it is good and then use the potential of this machine learning, that is deep learning is one of them, and apply these two so that that finally the final product of this rainfall simulation becomes more useful. So that is the overall idea. And with that, there are different some descriptions are shown here. So far as that and the hybrid that deep learning is concerned, and I think these are all you have already covered. That is what this the causal variability starts from. There are different conformal layer, then then the pattern layer, and then the MLP network is there, and finally we are getting that predicted rainfall for 5 days in advance. And this is how for the different cities like Akola, Amaravati, Aurangabad. So these are different cities are there, and how the performance is. If I just take only one, there are three different things are compared again. One is the support vector regression, deep MLP, and the hybrid conform 1D MLP combination of these two, and how their performance during the training and testing that we have checked for different stations. And there are three values are shown here. The first one is the correlation coefficient, second one is RMSE, and the third one is the NSE. Yeah, for these all 12 cities. And these are the different folds. I think there are a couple of folds are utilized, and this performance is compared for different folds. And this is in a pictorial form how these things, how the performance is there. So far as the lead time is 1 day, that is tomorrow, day after tomorrow, lead time 3 days, lead time 4 days, lead time 5 days. So one thing is common for all three things, that is the hybrid model, deep MLP and SBR, is that as the lead time increases, its performance decreases, as you can see, but that is expected also. But still, up to 5 days, there are some promise that can be usable. This kind of predictions are. Yeah, these are for different studies. And I think I have explained this one while giving the presentation. So deep learning has the potential to capture this nonlinear relationship between different variables in the hydroclimatic system, so that can be effectively utilized. But overall, the most important thing that I want to convey for this kind of study is that these GCMs are good, or any climate model is good at some for some variables, and it is not good for all. Particularly, if we just take it the primary, secondary, and tertiary kind of thing. So primary generally includes, for example, as I was telling you, that wind speed, pressure field, temperature, that kind of things are primary meteorological variables. Secondary, we can say that rainfall, soil moisture, those things. And tertiary, we may say as a drought kind of thing, which are a combination of the much more complex phenomena. So GCMs is good at the primary variable. So here, if we just utilize that simulation from there, and then I put it in some machine learning or machine learning framework, then the overall performance for the secondary variables also can be improved. This is one of such demonstration for this. There is another one, it's called the graphical modeling approach, and here we just want to show there are two things have already been done in this domain. One is that called the whatever the association that we see that may change over time. It is not only for the large scale influence. Recently we have published, though that is not shown here, it is for the local basin scale variables also. So sometimes this also become useful, that what about a time varying statistical model that for the prediction of this, maybe here it is showing as an example of this ISMR, another one we have shown as an example of the stream flow. So not going much in the details of this last part, but only one thing that I want to mention as an what is the concept basically. So most of the modeling scheme, what we do is that if this is my target variable, and we consider always as a saturated model. So saturated model, that means that the target variable and this input variable all are connected to each other. There is some relationship. Just take as simple as the multiple linear regression model. So whatever input that I have, I generally have some connection between this input and the target. But it can be shown that there are some variables, some connections can be omitted, and this is called the graphical, this is called the graph structure between this, or the conditional independent structure among these associated variables. So there are few variables are there which are directly connected to the target one, and there are few variables are there which are not directly connected to the target, but its information comes via some information. For example, if I have the runoff as an information, so far as the stream flow is concerned, that time if the wind field may not be important. Or say for example, the evapotranspiration is available to me, so that time the relative humidity may or may not be significantly important for the target one. And this is the number one. Number two is over time, this structure may also change. Over time means over a scale of a climatological scale, since this variable itself is changing its characteristics, so that their relationship may also change over time. So these are the two things. One is that input can also change, and the model parameters may also change. So in this case, which are directly associated with this target variable, we call it as a parent variable, and using this parent variable only we can proceed over the time, and if there is any change over the time, then of course that time has to be considered. We have to check that how frequent these things may change, and what is the temporal persistence of one graph structure that has been identified. So like this is the overall concept of that temporally varying thing. So as I was mentioning initially, it is the saturated one. Then depending on the different that edge exclusion differences is called, we can exclude one edge at a time and see that how the structure is there, important or not. And then finally we can just go for these things. So one that example that I was showing here, and we can check that different time frame over which the model or the independent structure remains useful or informative. Okay, so if I take that to 1 year, 2 year, 3 year, 4 years, in this case we have seen that 3 years is the best one. Then update and check whether that temporal persistence exists or not beyond 3 years or not. So considering the optimal time horizon, the 3 years, so depending on that model development period and other things will change. And over different time, the model itself can change, input variables as well as model parameter both can change, and this is what is called the over the time. Sometimes this teleconnection pattern also may change. This is one such example that has been shown here. So this is for the large scale. So for the zone, that is at the El Nino and the Equatorial Indian Ocean oscillation that has been shown. Similarly, for the local scale also, for example, we have taken one such system is called the stream flow, and it can be the non-stationarity in the hydroclimatic system that also is there. Very recently there are some interesting studies that has come. They directly say in the paper title itself, which says the stationarity is dead. Water management. Similar to the future of hydrology and evolving science for the changing world, as there is a change, and also disturbance hydrology, the preparing for the increasingly disturbed future. So that kind of things are coming now. So this is one of the solutions that we have seen is called the temporal network, the concept of the temporal network that can come. So there are multiple variables are associated in a complex ways that we already know, that is the atmospheric circulation pattern. There are some primary variables are there which are sea evaporation, air temperature, precipitation and all. There are some secondary variables are also important, and finally there are some tertiary variables are also there, like the droughts or floods and all. So the different methods of this graphical modeling or the basin networks, vine cupola can be effectively used to identify such networks and also refer to as a graph structure among the associated variables. And the thing is that I can have some structure like this at a particular time. So y is my target and how their relationship is. But over the time at some t plus delta, so this kind of dependence can also change, and it can happen at the local scale as well, and it goes on over the time. So this series of this network is basically called the temporal network structure, and which is known as the time varying networks also. These are characterized by the temporal links between these variables that may change over time, appear, it may disappear, or it may reappear again after some time, or it may change so far as the connection strength is concerned. It's not only the connection is significant, but at the same time it can be highly significant or moderately significant also. There is a connection strength is also there. So that connection strength, even if these connections remains in the second step, but their connection strength may change, and that connection strength may change the model parameters as well. So here is the graphical representation again about this different model development period and their testing period, and after some time it needs to be recalibrated from the G1 to G2, and this one is called the optimum recalibration interval. So this optimum recalibration interval means after how long you can wait till you need to relook at your model. So once you develop one model, do you think that it will run for eternally, which is impossible? Now, particularly in this changing world, we have to see, and that is what is the term is called that ORI, that is optimum recalibration interval. So depending on that, one such example that I can get again here that there are different variables are utilized: specific water temperature, soil moisture, relative humidity, pressure, rainfall, potential overflow, transpiration. These are the things, and one such typical graph structure how it looks like has been shown here. So for example, our target is the next time step stream flow, and there are different months, 12 different months are there. How for that each and every model development period, how these things are changing. So this is low, there is a different color set is basically showing that how the edge strength is the low, medium or high. And you can see that it is either appearing, disappearing, the strengths are changing for different months, particularly for the monsoon months was the initial target. At the same time, the other non-monsoon months also becomes important where it is stream is changing over time. Okay, I think let me stop here, and if you have some questions, I'll be happy to answer. And there are some of the further readings are also included here. Some of these publications from where most of the studies has been taken and presented today. So you can also, if time permits, you can have a look at this one also. Okay, thank you. Let me answer the screen first.
So the students, I would encourage you to ask me questions related to this topic to Professor Rajib Maity. If you also if you have any opinion, like any comments or any, if you want any small suggestion related to the project which you have started, but also you may ask if you consider it to be related to the topics which Professor Maity covered today.
Yes, so maybe you can proceed.
If there are no immediate questions, maybe Professor Maity, you can tell us a bit about some of the open problems in hydrology where you think that machine learning and artificial intelligence, where you see a big role of machine learning and artificial intelligence making a big difference in the.
Yeah. So what I can do is that I can share the PPT for the students to look at it once again if they want to have a look at it, and some of those publications that is listed there, they can just have a look at it. And at a later stage also, if they have some questions, they can send me email. My contact details are also there on those PPTs. So if they want to come back at a later stage, there I can help them all these their projects and other things also. So should I share that one in this chat window itself so that students can download it from there itself?
You can actually mail me the PPT. I will share it with them.
Okay, fine. Oh, but I have already clicked it, so it is also here. So if you want, I can send it to you by email as well.
It's okay. I'll do it. I've got it, so I'll share it with them. No problem.
Okay, fine. Yeah, I think I finished a bit early. Maybe 2 hours time was given. I think 1 hour 15 minutes or so it's taken, but I think it's okay, right?
Yeah, it's okay. Okay, Professor Maity. So thank you all for sharing your thoughts, like sharing the detail of your research with us. And I'm sure that some of the students will get back to you with some questions or maybe some small advice regarding the project which they are doing in the
Yes,
part of this
definitely.
subject.
Yes, definitely.
Okay.
Okay then. Thank you, Arthur, and thanks everyone. So, I can leave now, right?
Yes.
Okay.
Thank you, everyone. So,
Thank you, sir.
Ah,
so tomorrow is for the students. Tomorrow we will have the class at the regular time, 3 to 4.
okay. Bye.
Bye.